Yeah.
So we're good?
Okay.
So I'm going to move around, so I'm sorry if that makes your job boring. So I'm going to be presenting risk-averse multi-arm bandits, and this is work with my colleagues at INRIA Leonard Europe. Alessandro's right there if you want to bug him. So,
July 1st, by the way. It's July 1st, just want to point out.
oh, okay. Yeah, I just put the date I was talking, but I'll correct that. It's critical.
For your next talk on July 1st.
Yeah. So what I'll be presenting is the stochastic multi-arm bandit setting, just again to give you an idea of what that setting's about. I'll introduce the risk-averse multi-arm bandit problem, the way that's working, and then two algorithms, theoretical analysis and empirical results. So first, the setting. The standard setting is you have k independent arms, each characterized by distributions, means, and variances, all independent, finite time horizon n. And the notation I'll be using is xis for the sample, and this is just a sample that's drawn from the distribution nu I, so the arms distribution. And then tit, it'll be the number of samples observed from the arm I up to time t. So this is for the arm itself. And then the protocol, this is standard protocol, and what you have is you have from time t equals 1 to n. You have a learner, which is making a choice of which arm to select. It selects the arm, receives a noisy observation, and then the environment reveals that observation from the arm's distribution. And in the standard setting, what you have is the optimal arm being characterized as the arm with the largest expected value. So the optimal arm, I star, is the arm with the largest mean, and that's the way that they generally characterize the arms, as the optimal arms as well. So in the risk-averse setting, what we decided to do was take motivation from finance and the idea of portfolios and efficient portfolios, and we decided that it'd be a nice combination to have risk introduced as part of the optimality of the arm. So we can characterize the arm now, not just by the mean, but also by some sort of measure of risk. And this is directly motivated by the ideas of efficient frontiers and portfolios and optimal portfolios. Relevant literature that is related to our work, there's a very nice set of papers from Audibert et al. And Solomon et al. In the bandit environment with the standard setting, which is expectation maximization. And they do some really nice analysis on the distribution of the regret. And they show that there's certain risk associated to anytime policies or anytime algorithms. And they go really into detail about that, but they don't talk about changing the selection policy. They still characterize the arm as being, the optimal arm as being the arm with the maximum expectation. Then there's a paper by Evandar et al., and this is in the online learning setting. This is a full information setting, so it's not bandit, it's full information. And there's an introduction of risk aversion to this setting. And what's nice about this is that they use the mean variance and the Sharpe ratios to characterize the expert in hindsight that would be considered the best expert. And they have a result that's negative for this setting, and they have another setting they introduce, which is basically a localized regret. And the localized regret works, while the non-localized regret does not. And one thing that they talk about in this paper that was really interesting is, because it comes into our problem as well, is that there's this sort of volatility associated to the algorithm that is not characterized by, it doesn't come from the rewards that are observed. So this volatility, this sort of risk associated to the algorithm as a result of this risk-averse setting. And then the Wermuth paper is an online learning paper as well, and this is on variance minimization. So the goal of this paper was to attempt to find the minimum variance online, and you receive a covariance matrix, you give a set of weights and a vector, and you try to find the vector eventually that gets you the minimum variance. And they found a positive result in there. So how should we measure risk? This was something that we thought about, and there are a lot of different characterizations of risk. You can expect a utility, you can use Sharpe ratios, mean variance, all these different things. But we decided that one of the best ways to do this would probably try to stick to the historically popular Markowitz model, which is the mean variance model. And one thing about this model that is a concern, and some people noted, is the monotonicity condition, which is violated as a result of the variance. But because of the historical popularity and the fact that it's very commonly used in finance in these areas, we thought it was okay to use this as a characterization of risk. So this right here is the risk of an arm I. And what you have is the specific mean variance of an arm I, and the parameter rho characterizes the risk tolerance. So depending on the risk tolerance that you'd like to design into the problem for yourself, you can set this as different values to characterize that. So for example, if you'd like to go after a variance minimization setting, you can just set rho to 0. If you'd like to do mean variance optimization type of setting, you can go from 0 to infinity, and infinity drops it down to the expectation maximization or the standard setting. And we define the optimal arm in this setting as the arm with the minimum mean variance. So in the regular setting, you have the maximum expectation. In this setting, it's the minimum mean variance. And the idea is that the arm with this minimum mean variance is optimal because it characterizes the risk associated to the Markowitz characterization of the arm. So we define the regret of the algorithm according to the standard form, which would be the empirical regret of the algorithm versus the empirical regret of the optimal arm I star. And just to open this up to explain the different parts of this, the empirical mean variance of an arm I up to time n, the finite horizon, is just the standard form I was showing you before, and you have the empirical estimates for the mean and the variance for this empirical mean variance. And then for the empirical mean variance of the algorithm, what's very specific about this is that the algorithm is going to be observing a sequence of rewards associated to different arms. So what it's doing is you're calculating the empirical mean variance that is observed by the algorithm. And this is, that's the regret. So when you open it up, you can understand the influences the components that actually contribute to the regret. And what you see is the standard form of regret in the regular setting, the standard setting, is this setting essentially. But basically, it's the number of mean variance gaps between an arm and the optimal arm multiplied by the number of times you pull it. So this is the standard right here, just this section right here. But what happens is, in this setting, you have this other term, which in my opinion is very similar to the way that the paper by Evandar et al., they talk about the volatility associated to the algorithm. This is a very similar term because what you have is you have the variance of the means. And this term, it's a very interesting term because what it does is it characterizes the variability of the commitment of the algorithm. So essentially, the idea is that this term right here is a risk which is embodied in the risk of pulling the arm. So if I pull one arm many times, then I'm going to end up with a very low value for this. And then if I pull all the arms equally, then I'm going to have a very high value for this. And this is an animation. I'm going to just start it in a second, but just to set it up, what you have here is the number of times you've pulled arm 1. This is just a 2-arm example. And then I'm just assuming, okay, I pulled this one 0 times, and this is n times for the second arm, just so I can get a nice continuation here. So this is where this is right here. And then this is the mean for the first arm, and this is the mean for the second arm, and this is the empirical mean of the algorithm itself along this. So you can see as you watch the development of the risk, as the poles change, that as you start to get to the point where this empirical mean of the algorithm centers between the two means, you hit the peak of this regret. And the idea is that you really don't want an algorithm to do that. You'd like an algorithm that pulls one arm, it commits that arm, and it doesn't explore too much. So it actually learns something. And we thought, okay, well, a great way to deal with this would be to set up a confidence-bound algorithm, because then you can focus on pulling the optimal arm singly most, and at the same time, this should hopefully reduce the second term and the variability of the algorithm's regret, the variability in the regret. So this is just the standard confidence-bound style algorithm, and what you have is you have your time horizon from 1 to n, you have the different arms, you compute an index. This index is the empirical mean variance of that arm minus a confidence term. And this confidence-bound term is negative because we want to be optimistic so that we force some sort of development of the learning. So from this, you have the selection of the arm, and the arm with the minimum index is the one that's selected. And then this progresses. And to go into the theoretical analysis of this algorithm, I'm going to introduce the pseudo-regret first and discuss how that helps simplify the analysis and helps us with the analysis itself. So this is the pseudo-regret of the setting. And what you have, again, is this term right here. You have a reformulation of the second term. And this is, again, this is that at the standard regret from the standard setting. This is the exploration risk, or the pure risk of learning, or the variability of the algorithm itself. And what's nice about the pseudo-regret as in the standard analysis is that the pseudo-regret has a high probability relationship to the regret itself. And in expectation, this holds, so this allows us to do the analysis necessary for our proof. And what you have is you have the expectation of the pseudo-regret, which is in the O notation to simplify the way this analysis looks. And What you notice initially is that it does decrease with n. So the regret does decrease with n. But you have this term right here, this delta min term. And this delta min term is sort of tricky term that I'll show another animation to display that. So this is a no gap. This is a chart showing the decrease with n where there's a non-zero gap. So there's no zero gap in this setting. And what you have is you have the three different terms of the regret, and they're all decreasing with n. And then you have a trivial setting which can really show the effect of this delta min term. And the delta min term is something interesting because it kind of highlights this effect of having a zero gap, which would be it kind of forces that second term to really increase. And what you have in this setting, it's a very simple setting where we have two arms. We set it for a variance minimization setting, so rho is equal to 0. The means are different, so there's a gap in the gamma. And then there's equal variances. So essentially the terms, it turns into it reduces the index down to just being about the confidence term. So this is all you have. So essentially what happens is the algorithm is going to get forced to arbitrarily select and just in expectation equally pull both arms. So it won't commit. And what this should show is, so if they're pulled equally, then this reduces to a constant regret, which again reminds me of the Evandar paper and how they talk about the nature of the constant regret that they had. And you can see it in the demonstration here for the mean variance lower confidence bound algorithm, the different terms. So this term is zeroed out because essentially we've got no gap, but the other term is still there, and this little gap here has to do with the small O term in the regret. And it's pretty much constant. And we didn't like this, but this right here, you can set this up for you. Basically, this is the variance gaps from 0 up to 0.25. So this region right here, the gaps are very, very small, 0.001. And this is the mean gap from 0 up to 1. And this is just the surface of regret. So this regret surface, as you see in the animation, it changes, and there's a certain region which just doesn't decrease. And this region right here represents that second term, or the effect of having that zero gap and not being able to commit to an arm, and the effect of that sort of variability of the algorithm. But this is kind of the worst case right here, the kind of a worst case zone. So what we thought was, how can we focus this algorithm on selecting an arm and really committing to that, forcing it to do that? So a simple way to do that is the exploration exploitation algorithm. And this is just simply, you take a tau term, it's an exploration term, so you have this phase, you equally pull the arms during this phase, and then you use the information from this phase to determine which arm to commit to. So this is the arm that's selected after this exploration phase, and now we exploit that arm. And the regret is much nicer. There's an upper bound on the regret. So this has a guarantee which is nice, and it's for any choice of distribution. So it presents a nice guarantee of performance that you can't get in the MVLCB algorithm. And you see the comparison here. You see how X decreases with N nicely, and how MVLCB has a lot of trouble with this setting. So it solves that issue. And one thing we would really like to see is if it's possible to create one algorithm that can perform with these kind of guarantees, but with the speed and the performance of MVLCB in the other areas. So again, this is the X regret grid. So you can see the way that this performs, and it performs nicely, and you see it decreasing nicely throughout the grid. So there's no region of concern. And if I run this further, you can see N right here is 250,000. If you run it to 500,000 to 1 million, you'll see it basically flattening out. And the values are very small for the regret. This is 10 to the third, 10 to the negative third. It's very small. So what about scaling to more than 2 arms? How can we apply this to a case where you have a sort of a large selection of arms? What we have here is you have the variance along the bottom, and then you have the means on this side right here. So this is a mean versus the variance. So this arm right here has very low variance and very low mean. And these are just arms, these news throughout the chart. So these are arms. So the arms on this bottom section are dominated by this frontier of arms along this pink line, this pink frontier. And what this pink frontier represents is the frontier of row values that you can select that characterize different kinds of risk. So for example, some of the arms are optimal for, this is optimal for this setting of row, while it's not for this one, and this one would be.
Is this something like Pareto front?
You could, I think, I think of it as an efficient frontier, sort of like the, efficient frontier type charts. I guess you could think of it like that.
So I mean, the fact that you're using Markowitz is kind of problematic, right? Because there are things that dominate, not even stochastically, just strictly dominate arms, but because they have high variance, and therefore they're always better,
Right.
the outcome that you get, they would not be, they're not in your efficient frontier, which is like a weird way of
Yeah, I mean,
finding efficiency.
right.
I feel better when I pull this arm, but you're telling me that that's not the efficient arm to pull.
Right. Well, I think that the way to think about it is, when you look at it as just being a setting to choose which arm to make, as your selection, and you're choosing these arms, you might have that situation where it's not even on there.
Yeah, there's an arm that always gives me $1, and there's an arm that gives me $1 billion or $1 million.
Right.
Okay, you're telling me the efficient one is the arm that gives me the $1 every time for sure.
Well,
For some parameter.
right, for some parameter. But the idea is that it's not really a portfolio either. It's more of like the portfolio in the sense that you have these arms and you're selecting these arms and you just want to kind of converge to the arm that has this trade-off in itself intrinsically. So I don't know if I completely understand what you mean. We can talk about it though. But this is just to show if I had a selection of row that turned this arm as being the optimal arm, then you'd hope that these two algorithms would converge slowly to this. So these are the two algorithms, and you can see the way that they perform with these different values of rho. And you notice that the MVLCB algorithm, the blue algorithm, the distance between the frontier on the blue algorithm and the pink frontier is the regret. So, for this point in that algorithm and that selection of rho, you can't really pull an arm that's not in the existing selection of arms, but it's slowly converging, and you see it nicely converging here to that arm. And this is the exploration exploitation algorithm, which is different. So this one had a period where it was exploring, and then it just kind of grew with a nice shape. So we introduced a risk aversion setting in the Bandit case, in the Bandit problem, demonstrated two novel algorithms, provided theoretical analysis, presented empirical results, and opened some new and interesting theoretical questions. The extensions in the future work, right now we're working on a lower bound, and there are other compatible risk measures which would be better. We just thought this was historically popular, so we might as well use the catchy name and these sort of things. So you can always use absolute deviation, Sharpe ratio, expected utility, value at risk, conditional value risk, expected shortfall, and there's tons of different ways of doing this. And then there are other bandit problems. So you have linear bandits, which would be more of a kind of a portfolio optimization type of situation, because now you're choosing a selection over a vector. And then you have the contextual bandit case, and there are other bandit problems as well that I'm sure we could apply this to. So that's the risk-averse setting.
Do you have any questions? We got plenty of time.
So how specialized is the theoretical analysis to the Markowitz?
It's arbitrary with the Markowitz. I mean, you have the Markowitz, you open up the regret terms, and then now you have this gap. So it changes the analysis a little bit, but I think when you change the way that you characterize the risk, it just changes the way this gap is characterized in the, where is it? So we have so this is our regret. So I guess if you were to change it from mean variance in the Markowitz sense to something else, it would just change this, but then you see that when you get to the gap, this is just the gap in the mean variance right here. So
just plug
in a sense, it wouldn't be too hard to change it and just change the regret with a simple change in the risk measure. The more interesting part about it is really this, and this is something that came up in the Evandar paper, not this specific term, but this sort of variability in the regret in the algorithm.
But that looks fairly independent of the underlying.
Yeah. The Markowitz, I mean, you can turn this to,
At least the symmetric case, right, or the upside risk.
Right, exactly. Right. Any other questions? Cool, thank you.
Thanks a lot.